How to identify gold in quartz, geological methods and field tips. Deep in the heart of the earth, nature hides one of its most valuable treasures, gold, often locked within the veins of quartz rock. But how can you, as a geologist, a prospector, or an adventurer, distinguish real gold from the glitter of fools? In this video, we're diving into the fascinating world of gold-bearing quartz. You'll learn how to identify real gold in the field using proven geological techniques, simple tools, and expert field tips. Whether you're out in the wild or working in the lab, these insights could be the difference between striking gold, or being fooled by pyrite. Let's get started. What is gold in quartz? Gold in quartz is one of the most iconic and visually stunning forms in which gold naturally occurs. But what exactly does that mean? Geologically speaking, gold often forms deep underground, in hydrothermal veins where hot, mineral-rich fluids travel through cracks in the Earth's crust. As these fluids cool, minerals like quartz begin to crystallize, and in some cases, microscopic to visible flakes or even veins of native gold become trapped inside the quartz. These quartz veins can be found cutting through host rocks like granite, schist, or even basalt, depending on the regional geology. In some rare cases, the gold is so pure and concentrated that it can be seen glimmering to the naked eye, what prospectors often call visible gold. More commonly, though, gold is present in smaller, scattered inclusions or microscopic grains that require careful examination and sometimes lab analysis to confirm. What makes this form so special is that it's a direct result of geological processes, temperature, pressure, and fluid chemistry all coming together in just the right way. And for geologists and gold hunters alike, spotting gold in quartz isn't just exciting, it's a clue to something much bigger, the potential for a valuable mineralized system nearby. So how can you tell if that shiny material in the rock is the real deal, or just fool's gold? Let's find out. How to identify it in the field. So, you're out in the field and you come across a quartz vein running through the bedrock. Could it contain gold? Here's how geologists approach that question step by step, using visual clues, physical properties, and simple field tools. First, look closely at the quartz. Gold-bearing quartz often appears milky or glassy white, and it may contain rusty iron staining from sulfide minerals like pyrite or arsenopyrite, both of which can be associated with gold mineralization. These iron oxides can signal that hydrothermal fluids once moved through the rock, the same fluids that often carried gold. Next, check for visible gold, sometimes called free-milling gold. Real gold in quartz appears as small flakes, threads, or even tiny nuggets embedded within the quartz structure. It will usually have a rich, buttery yellow color and a soft metallic luster. Unlike pyrite or mica, real gold does not sparkle like glitter. Instead, it glows gently and does not reflect sharply in the sunlight. Now, grab your hand lens or a jeweler's loupe. This is an essential field tool. Under magnification, gold appears malleable and smooth, while pyrite tends to form sharp cubic crystals with brassy reflections. Gold also tends to sit flush with the quartz surface, whereas pyrite might protrude or weather away more easily. A quick field test you can perform is the hardness test. Gold is soft, only about 2.5 to 3 on the Mohs hardness scale, which means you can scratch it with a copper coin or a steel knife. Pyrite, on the other hand, is much harder and cannot be scratched so easily. Another field indicator is density. Gold is very heavy, about 19 times the density of water. If you break off a small piece of quartz with suspected gold, it may feel unusually heavy for its size if real gold is present inside. Of course, field identification has its limits. Many samples require lab analysis to be certain, especially when gold is microscopic or finely disseminated. But in many cases, these field clues can help you determine whether your find is worth investigating further. Coming up next, we'll explore how lab and advanced methods can confirm your field observations, and tell you if you've really struck gold. Laboratory and advanced methods. While field observations can give you strong clues, confirming the presence of gold in quartz with confidence often requires laboratory analysis. Especially when gold is finely disseminated or occurs in subvisible forms, lab methods offer precision, quantification, and mineralogical detail that the naked eye simply can't provide. One of the most commonly used tools in modern exploration is the X-ray fluorescence analyzer. This portable device can detect trace elements in rock samples within seconds. Although X-ray fluorescence is not ideal for detecting very low concentrations of gold due to its low atomic number, it's extremely helpful for identifying associated pathfinder elements like arsenic, antimony, copper, or tellurium, all of which can point to gold mineralization zones. For actual gold quantification, fire assay remains the industry standard. It's a centuries-old technique still used today because of its high accuracy. The sample is pulverized, mixed with fluxes, and heated to extreme temperatures. The gold separates and is collected in a lead button, which is then refined and weighed. Fire assays can detect gold concentrations down to parts per billion, making them highly reliable for even the tiniest amounts of gold. Gravimetric analysis is another classical method used especially for high-grade ore samples. After dissolving the sample and removing impurities, gold is precipitated out, filtered, dried, and weighed. This method is slower but very accurate for visible gold occurrences. In academic and research settings, scanning electron microscopy combined with energy dispersive X-ray spectroscopy can provide high-resolution imaging and elemental composition at the microscale. This is especially useful when gold is trapped within sulfide grains or intergrown with gangue minerals like quartz. Another useful method is atomic absorption spectroscopy or inductively coupled plasma mass spectrometry, which are excellent for multi-element geochemical analysis and trace-level gold detection. These techniques are widely used in mineral exploration, or deposit studies, and resource estimation. For structural and spatial studies of gold distribution, thin-section petrography and reflected light microscopy allow geologists to analyze ore textures, mineral associations, and alteration patterns, providing insight into the geological history of the deposit. Ultimately, combining your field observations with the right lab methods gives you the complete picture. It's not just about whether gold is present, but also how much, in what form, and what it tells you about the geology of the area. That's the power of integrating field geology with laboratory science. Gold versus fool's gold, pyrite. One of the most common challenges in the field, especially for beginners, is telling the difference between real gold and what's often called fool's gold, pyrite. At a glance, they can look similar, especially under sunlight when both reflect light. But with a trained eye and a few simple tests, the differences become clear. First, let's talk about color and luster. Gold has a deep, warm, buttery yellow hue. It doesn't sparkle, it glows. It reflects light with a soft metallic shine that stays consistent from every angle. Pyrite, on the other hand, has a brassy yellow tone that can sometimes appear greener or darker. It sparkles sharply when hit by direct light due to its crystalline structure, which is a key giveaway. Now let's look at crystal form. Pyrite commonly forms in well-defined cubic or pyritohedral crystals, often with sharp, straight edges. Gold rarely forms such perfect shapes in nature. Instead, it occurs as irregular flakes, wires, or rounded nuggets. If you see cubes, you're most likely looking at pyrite. Another difference is hardness. Gold is very soft, about 2.5 to 3 on the Mohs scale. That means you can scratch it with a copper coin, steel nail, or even gently with a knife. Pyrite, in contrast, is much harder, around 6 to 6.5, and cannot be scratched with common tools. In fact, pyrite can scratch glass, while gold cannot. One of the most telling tests is malleability. If you take a small flake and try to bend it, real gold will deform and flatten without breaking. It's ductile and malleable. Pyrite, on the other hand, is brittle. It will crumble, shatter, or break into powder under pressure. This is a crucial field indicator when visible gold is suspected. You can also perform a streak test. Drag the mineral across an unglazed porcelain tile. Gold will leave a yellowish or golden streak, while pyrite will leave a dark greenish-black to brownish-black streak. Finally, weight is a clue. Gold is extremely dense, over 19 grams per cubic centimeter, so even a small piece feels unusually heavy for its size. Pyrite, though metallic, is significantly lighter. So while pyrite may fool the eye from a distance, up close it gives itself away. For geologists and prospectors alike, understanding these differences isn't just academic, it's the difference between empty dreams and a real gold discovery. Where to search for gold-bearing quartz. So you've learned what gold in quartz looks like and how to identify it, but where should you actually go to find it? The truth is, gold-bearing quartz doesn't occur randomly. It forms under very specific geological conditions, and if you know what to look for, you can dramatically improve your chances of success. First, gold-bearing quartz is typically found in regions with a history of hydrothermal activity, areas where hot fluids once circulated through the Earth's crust, depositing minerals along fractures and faults. These fluids often create quartz veins as they cool and precipitate silica. When gold is part of the mineral load, it becomes locked within the quartz. Start by studying ancient tectonic belts and orogenic zones, places where continental collisions occurred in the geologic past. These regions often contain greenstone belts, metamorphosed volcanic sedimentary rocks, and shear zones, all of which are prime hosts for gold mineralization. Examples include the Mother Lode Belt in California, the Canadian Shield, the Yilgarn Craton in Australia, and the Birimian formations of West Africa. Also, pay attention to fault zones, folds, and contact zones between intrusive and country rocks. These structural traps often act as conduits for mineral-rich fluids. Quartz veins within these zones, especially those with iron staining, sulfide minerals, or brecciated textures, are excellent places to investigate. If you're exploring on a smaller scale, look for erosion-exposed quartz veins in hillsides, creek beds, or along road cuts. Often, the gold-bearing veins have weathered over millions of years, and fragments have washed into nearby alluvial systems. This is why placer gold in rivers and streams often points upstream toward hard rock sources like quartz veins. It also pays to research the mining history of your region. Old gold districts, even those considered worked out, may still hold overlooked veins or modern potential through new methods. Access historical geological survey maps, old mine reports, and local academic research. These often contain valuable data about host rocks, mineral trends, and/or bodies. In recent years, satellite imagery, drone surveys, and geochemical soil sampling have added powerful new layers to gold exploration, but nothing replaces boots on the ground and a trained geological eye. And remember, not every quartz vein contains gold, but gold rarely occurs without quartz nearby. So always examine the broader geology, alteration halos, nearby sulfides, structural controls, and regional stratigraphy all help tell the story of whether a quartz vein has potential. In the end, finding gold-bearing quartz is part science, part skill, and part patience, but when the clues align, it's one of the most exciting moments in field geology.